Hello there, space traveler. Tonight I ask, how far can humanity really go? Not just to the moon or the nearest star, but to the very edge of what physics will ever let us touch. How far from home can humanity go? How much of the universe can we access and know? And what will we learn from it? The universe is huge, but how huge is it? But first, leave a comment. What's the furthest you've ever traveled from home? Have you ever left your state? Or your country? Or even your planet? And don't forget to follow and like the channel so we can continue the project. You'll all travel alongside Captain Astreus for a few quiet moments as if you were on these missions. We'll map light cones to see what parts of the universe can never meet us. Watch space itself expand as distant galaxies slip away, and use moving distances to keep our cosmic rulers from stretching in our hands. We'll all draw two boundaries. You'll hear again and again. The observable universe, everything we can see, and the reachable universe, everything we can still influence. We'll talk ships. Why chemical rockets won't get us far. What nuclear, electric, fusion, and beamed sails could really do. And why slowing down at the destination matters as much as speeding up. We'll explore self-replicating probes that might quietly stitch a civilization across the stars. And we'll all imagine the maximally observable universe, a future where every reachable star becomes part of one vast telescope. So settle in, dim the lights, get comfortable. If your eyes get heavy, don't fight it. Some stories are best heard half asleep. But if you stay awake, you'll carry something new. A quiet knowing, a path that feels like yours. And maybe even the hum of the road calling you forward. Ready? Captain Astreus is waiting at the airlock. Let's take the first step. Captain Astreus drifts in the windowed cupola of his ship while Earth unrolls beneath him. Storm swirls. City necklaces. The slow blink of dawn across the Atlantic. One gloved knuckle taps the glass, not at a country, but at a feeling. Home used to fit inside the walls of a room, he says softly. Then a city, then a planet. He traces 3 invisible rings in the air, the tight sprint of low Earth orbit, the high lanterns of geostationary satellites, the gray curve to the moon, and lets the cabin lights dim until only the limb glow of Earth remains. He takes a breath, turns toward us, and smiles like someone about to pull back a curtain. Let's see how far we've really gone. Now the story steps aside, and the universe steps in. We will measure everything the only way the cosmos truly respects. In light. Light is the fastest messenger allowed. If light can't get there in time, neither can we, nor our ships, nor our bravest plans. Start close. A spacecraft in low Earth orbit lives a few hundred kilometers up, so near that a photon would cross that gap in a little over 1,000th of a second. Blink, and you've already outrun the station. Farther out, geostationary orbit 36,000 kilometers. Above the equator holds weatherbirds and TV satellites steady over one longitude. A radio ping takes about 1/4 of a second to go up and come back, just long enough for a human pause. Then the moon, 384,000 kilometers away, 1.28 seconds of light time. You can speak, count 1 Mississippi. and hear yourself return from another world. Apollo 13's far loop around the far side still marks the outer edge of human bodies in space. Roughly 400,000 kilometers, about 1.34 light seconds. Close enough to see continents with your eyes, far enough to feel profoundly alone. Those rings are distances? Yes, but they are also classrooms. Low Earth orbit taught us survival grammar. Breathe air you cleaned yourself. Drink yesterday's water. Fix the thing that's keeping you alive without turning it off. Geostationary altitude taught us to watch home as a single living system. Cyclones knitting, forests browning and greening, cities dimming under blackout and brightening again. The moon taught origin, a hot, violent earth newly formed, a moon co-born from the wreckage, dust that loves seals and hates lungs. And while our bodies stayed near, our machines went far. We rolled robot geologists across Mars and found riverbeds on a world with no rivers. We blinked for minutes on Venus before the heat ate a lander. We sailed a methane sea in our minds because a probe tasted rain on Titan. We kissed comets and scraped asteroids and sent tiny labs to read the recipes that built planets like ours. Farther still, 2 bottles in the deep, Voyager 1 and Voyager 2. They fell past Jupiter and Saturn, then slipped through the sun's last slow breath into interstellar night. One now sits more than 20 light hours away. You don't converse at that distance. You exchange letters. Taped to each craft, a golden record. Thunder and wails. Greetings in many tongues. A batch prelude. A scratch and hum of our rain. Sometimes the bravest way to measure distance is to decide what you would say to a stranger you will never meet. Anchor those feelings to a cosmic clock you can hold in your head. Sunlight takes 8 minutes and 20 seconds to reach your face on a winter afternoon. Pluto is hours away, about 5 to 7 light hours, depending on where it is along its long track. The heliopause, where the solar wind gives up and the interstellar medium begins, sits roughly 16 to 18 light hours out. Voyager beyond 20. Those aren't just numbers. They're delays you can feel. Somewhere between we can talk and we can only wait, your instincts flip and the night becomes geography. So what exactly have we touched? 4 honest footprints. First, where humans have been with boots and breath, the moon. Second, where our machines now live, interplanetary space, and thanks to 2 stubborn spacecraft, interstellar space. Third, where our senses have reached, telescopes that drink ancient light, letting us see billions of years into the past. Fourth, where our influence has arrived, a whisper-thin bubble of radio snow, roughly a century old, and on the order of 100 light-years across at its faintest fringe. Too weak to impress anyone, but real enough to mark that we were here. If that sounds small beside a universe that has no edges you can point to, remember what those small steps bought us. Low Earth orbit is not a destination. It is a workshop where we learn closed loops and constant maintenance, the basic verbs of living anywhere else. The moon was not a flag. It was a geology class in the language of worlds. The robot decades taught us patience, autonomy, and how to see for a very long time without blinking. Each ring outward changed not just what we know, but who we believe ourselves to be. Leaving home does what leaving home always does. It makes you look back, compare, and plan. And planning matters, because distance is not the only plot twist. Time is too. Our travel budget is written in light time, but our destinations move. Earth spins, orbits the sun, bobs through the solar system's drift. The sun orbits the galaxy. The galaxy swims through a sea of other galaxies, and that sea itself is stretching. Later, we will draw the cones that show what can ever reach us and what we can ever reach. For now, keep one truth close. The farther you go, the more the map itself tries to walk out from under your feet. Still, it is worth asking, what did leaving do to us? Astronauts talk about the overview effect, the way your chest goes warm and your voice goes quiet when you first see Earth whole. No borders, only watersheds and weather. A thin cradle of air you could rub away with your thumb if you got the angle wrong. You come home changed. From orbit, we watched dust plumes cross oceans, saw rivers brighten and dim, learned that a wildfire in one country is a haze in another's lungs. From lunar distance, we took the most useful self-portrait in the species album, Earthrise over a dead horizon. It did more than win awards. It funded laws and habits. It said with a picture what whole libraries had been trying to say, that this is a single place, that sober counts live beside silver poetry. In a century of flight and a lifetime of rockets, only on the order of a few hundred people have traveled high enough to be called in space, and only a handful dozen walked anywhere other than Earth. Our machines get the mileage because they can be patient in ways we cannot. A rover can winter on a Martian slope for months until the sun returns. A probe can do quiet math in the cold between stars for decades. They do not need coffee, jokes, or a window. We need all three. And yet be honest with your hope. This is how you scale. Humans tackle the near and delicate. Decide, design, test, and teach. Robots bear the long, rough distances. Endure, sample, fail, repeat. Together, they draw the first real map of what reachable will mean for centuries. If you want to know how far we can go, look first at where we already are. Stations circling in low Earth orbit, a whisper-thin radio shell riding outward at light speed, twin elders Voyagers sending back the hard-won news that space between the stars is not empty but patient. Now come the handholds you will grab in every chapter that follows. Light as the speed limit. Distance counted honestly in seconds, hours, and years of light time. Moving targets. Planets in orbits, stars in streams, galaxies in a current that speeds up as the universe expands. And horizons. The kind you've seen at sea, and the kind you can only draw in space-time, telling you what can ever touch you and what forever cannot. We'll also keep one more lens polished, humility. For all our pride, we are at the plank edge of a vast pier. Low Earth orbit is close enough that our voices still sound like ourselves. The moon is an echo and a heartbeat away. The rest for now is letters and instruments. That doesn't make the story smaller. It makes the next pages honest. Because to talk about how far we might go, you must first accept the one rule nobody has ever broken. Nothing with mass outruns light. Not your best rocket. Not your bravest ship. Not even your plan. Reality check, spoken plainly. The farthest a human body has traveled from Earth is roughly 400,000 kilometers, about 1.3 light seconds. The farthest active spacecraft are a little over 20 light hours away. The edge of the sun's influence, the heliopause sits under a day of light time. Our fastest probes cross one astronomical unit the Earth-Sun distance in months, not minutes. Interstellar travel, for us, is not a 2020s problem. It is a multi-century engineering lineage. Budgets and risk tolerance shape these realities as much as physics does. Launch costs, flight times, radiation, the grind of maintenance. None of them care how inspiring your storyboard is. The good news is that the toolbox we really need: closed-loop life support, autonomous repair, energy thrift. Patient navigation was born the day we learned to live in low Earth orbit and sharpened every time. A robot took a perfect picture 1 billion kilometers away. The map is large. The curriculum is working. Back in the cupola, Pastrius watches sunrise pour across the Pacific like hot metal. City strings blink out. The stars fade. Home, he says, is larger than it used to be. He gives the window one last tap: ring 1, ring 2, ring 3, and pushes off toward the flight deck. We'll follow him later. For now, the camera stays with the Earth and the air just above it, where our story began, and the voice that's been guiding you drops one last breadcrumb. If light is our fastest coin, how far can we spend it? In the next chapter, we'll draw the shapes that decide the answer light cones that outline the parts of the universe that can never touch us, and the parts we can never touch. Once you see those lines, every other limit, every possible path, and every honest dream will make a new kind of sense. The observatory is dark enough to hear your own breath. Captain Astreus fogs a pane of backlit glass and with a gloved finger sketches 2 cones that kiss at their tips, one opening upward, one downward. At the rim, he writes a single letter, C. This, he murmurs, tapping the lower cone, is everything that could ever have reached us. A tap on the upper cone, and this is everything we can ever reach. He studies the glowing geometry for a beat, then smiles to himself. Understand these shapes, and you understand what's possible. He sets the marker down. We step back from the glass out of the hushed room and into the wider frame. Listen closely. The universe enforces a speed limit, and it isn't a polite suggestion. In vacuum, light races at about 299,792 kilometers per second, a constant we call c. Relativity says anything with mass that tries to catch light discovers an impossible build time dilates. Lengths contract, and the energy required to go just a little faster swells without bound. You can flirt with C. You cannot marry it. Now picture a simple map of reality. Put yourself at the center here now. Let the vertical direction be time, the horizontal spread be distance. From your point, draw the steepest possible lines anything can travel, the paths of light. Spin those lines into 3 dimensions and you get two hollow cones meeting at their tips. The one opening downward is your past light cone. Every event that could have influenced you by sending a signal at or below C that arrives exactly now. The one opening upward is your future light cone. Every event you can ever influence, even if all you do is whisper with photons for 1 trillion years. Outside both lies elsewhere, a region that is not merely far, it is causally disconnected. No push, pulse, or prayer can jump there without breaking the rules. These cones aren't metaphors. They are the operating system. They explain why now, on Earth, and now, at Alpha Centauri, are slippery ideas that depend on motion. They explain why there are no perfectly rigid rods that shove here and move there instantly. Mechanical pushes are waves in matter, and waves in matter obey the speed limit. Even gravity respects the changes in gravity, ripple outward as gravitational waves at sea. Make it concrete. Aim at Alpha Centauri, about 4.3 light years away. A message you send today can arrive no sooner than 4.3 years from now. A reply no sooner than 8.6 years from now. If your friend lives there, the only possible meetup must sit inside the overlap of your future light cone and theirs. If the cones don't overlap at some place in time, you will never meet no matter how brave the plan or shiny the ship. Zoom inward, and you already feel the cones in everyday spaceflight. The moon is 1.3 seconds away by light. Conversations have a heartbeat of delay. Mars, between roughly 3 and 22 minutes one way, depending on orbits. You don't talk to a rover, you write letters. Jupiter takes tens of minutes, Pluto hours. Nothing is wrong with our radios. That lag is geometry made audible. Zoom outward, and the cones start drawing the borders of knowledge and ambition. Your past cone carves out the observable universe. Everything that has had time to beam us light since the hot beginning. Your future cone marks the reachable universe everywhere our signals or ships can ever, even in principle, touch. Later, we'll lay cosmic expansion over this diagram and watch those surfaces bend and bow. But the skeleton is already here. In a relativistic universe, cause and effect are local, and elsewhere is real. There is one more subtlety worth holding. Motion and strategy can change what lies inside your reach. Accelerate hard, and your future cone, as seen by you, opens onto slices of the world that were previously out of play. Idle, and opportunities slide away. The speed limit never budges, but good navigation leaving sooner. Aiming smarter decides whether a rendezvous lands inside the overlap or slips into the unreachable gray. So when Astrea sketches cones on glass and writes C at the rim, he's not doodling. He's drawing permission and prohibition. Inside the cones, you may if you can afford the time and energy. Outside, you may not unless you can change physics. Reality check. There are no verified shortcuts. Warp drives and traversable wormholes do appear in honest equations, but every design we know demands exotic matter or sustained negative. Energy densities we have never created at meaningful scale and may never be able to. Quantum entanglement can't smuggle messages faster than light. It trades correlations, not information. Claims of superluminal anything have always reduced to tricks like outrunning light in glass or water. Cherenkov glows, while still losing to light in vacuum. The limit stands, and latency is permanent. A hello to Proxima Centauri takes approximately 4.2 years to arrive. The highback returns approximately 4.2 years after that. Within our own system, Mars chat lives on minutes of lag. At the Kuiper Belt, it's hours. Deep space will always feel like letter writing. That's not a flaw to be engineered away. That's the shape of the cones. Plan accordingly. Autonomy on board, patience on the ground, and mission designs that treat delay as a first principle. The dome is almost dark. Captain Astreus lowers the lights until the Milky Way looks like powdered silver across black glass. On his console, a spectrum unfurls thin, colored lines nudge toward the red. He places another dot on a growing chart. Distance along the bottom, apparent recessional speed up the side. The points don't scatter. They climb in a calm, straight slope. He murmurs, almost apologizing to the night, that the galaxies aren't flying through a fixed stage space itself is carrying them away. The stars keep their secrets, but their light does not. It arrives stretched, slowed, reddened. He draws a small circle around our local group, then wider and wider rings that enclose fewer familiar islands and more thinning dark. The camera drifts over his shoulder. The starlight remains, but gentle graphics settle over the scene the way captions do in a museum no hard cut, just a layer of clarity. Stay with this simple picture. Along one axis, distance. Along the other, how fast a galaxy seems to recede. Astronomers noticed long ago what Astreus is tracing. The farther a galaxy, the faster it recedes on average. That relation, often written as a speed equal to today's expansion rate times distance, is the Hubble-Lemaître law. The crucial shift in intuition is this: galaxies are not tiny rockets streaking through stillness. The stage itself is growing. Imagine dots on a rubber band. Stretch the band, and every dot moves away from every other dot. No dot sits at a privileged center. From anywhere you stand, the expansion looks the same. Light carries the proof. Waves that left a distant galaxy departed with a particular color. By the time they reach us, the universe has grown. The wave crests arrive farther apart, the wavelength longer, the color shifted toward red. The larger the redshift, the more the universe expanded while that light was en route. Then came the twist. At the turn of the millennium, we learned the expansion isn't merely continuing, it's accelerating. Something we call dark energy urges the fabric outward ever more strongly with time. In a cosmos like this, far does not just mean it will take longer. Sometimes it means it will drift beyond anyone's reach. Two quiet boundaries help us think straight without breaking the spell of the night. The first is the Hubble sphere, the distance at which, right now, recession due to expansion equals the speed of light. Farther than that, distant regions recede faster than light, not because anything outruns light through space, but because the space between swells. Photons launched toward us from beyond that sphere can still make it here if, as time passes, the sphere grows and eventually overtakes them. The second boundary is stricter and lies in the future, the cosmic event horizon. It marks the farthest place from which a signal sent today could ever reach us, even given unlimited patience in a universe whose expansion accelerates. It also marks how far our ships and messages can ever matter. Inside lies in principle reachable. Outside lies forever separate, not by lack of courage, but by the geometry of the stage. Let the map widen the way a documentary would. Begin with the Milky Way and the handful of galaxies bound to us by gravity. Within a few million light years, mutual pull wins. Space may expand, but these islands cling together. Pan outward into the broader web, and you see slim threads of galaxies drawing apart over eons, like slow currents across a deep ocean. Overlay faint arrows pointing outward, and watch them lengthen with distance. That's the expansion in motion. Then tint the view softly beyond a certain radius, a barely visible shell to suggest the event horizon's meaning. Anything already inside can still trade messages with us in the ages to come. Anything already outside will never share a two-way future with us, no matter how early we depart or how perfectly we navigate, so long as the same physics holds. The consequence is both austere and beautiful. As acceleration continues, more and more galaxies move from maybe someday to never. The horizon isn't a wall you can fly to and touch. It is a moving line in the equations that steadily edits the list of places we might one day visit. Today, we still catch the ancient glow of very distant galaxies, whose early light is only now arriving. Seeing, however, is not the same as reaching. Their newest light will never catch us. A ship launched now would chase a target the universe keeps easing farther away. If analogies help, picture a shoreline you're running toward while the sea rises faster than your best sprint. Near landmarks remain attainable. Distant ones drift away no matter how early you start, or return to the balloon, but with care. Dots painted on its surface separate as you inflate it, and there is no central dot on that surface. The picture captures the pattern of growth without suggesting there is an outside we could step into. Project the story forward. Our local island Milky Way, Andromeda, and a small retinue will merge and hold together. Farther out, the night very slowly thins. Over billions and then trillions of years, galaxy by galaxy, the universe beyond our island fades from the sky. Not because those places cease to exist, but because their light is stretched beyond detectability and their distance grows beyond communication. The chart Astria's started distance along one axis, recessional speed along the other quietly encodes that destiny. A vertical line marks where recession equals light speed today. Another line, set by dark energy, marks the event horizon that decides what can ever matter. The first tells us how things look now. The second whispers what can still be part of our story. It's natural to ask whether leaving earlier, traveling faster, pushing harder might change the verdict. Timing does matter. Starting sooner keeps more galaxies inside our shared future. Waiting too long lets acceleration carry them past the line where even patience can't help. Later, When we talk about strategy humans, fleets, and autonomous probes, we'll treat that timing the way mission designers treat launch windows. For now, let a simpler truth settle in. In an expanding, accelerating universe, distance and destiny are intertwined. Farther usually also means faster away, and in many cases, later quietly turns into never. Reality check, softly spoken before we dim the graphic overlay and return to the stars. This isn't a mood, it's measurement. We infer expansion from the redshifts written into galaxy light, and we map the acceleration with multiple independent tools, standard candle supernova, the ripples frozen into the cosmic microwave background, the pattern of how galaxies cluster across space. They agree. Recession speeds exceeding light are not rule-breaking rockets. They are what happens when the metric itself grows. Chasing a galaxy beyond the event horizon is not like missing a train. It's like racing a shoreline while the tide rises faster than you can run. In practical terms, that means our best engineering matters most close to home, where gravity and opportunity still meet. And it means the cosmic invitation, though long by any human measure, is not open forever. In the next chapter, we'll pick up better rulers for this stretching stage co-moving distance and the horizons that keep our maps honest as the fabric grows. So Astraeus chart and our plans don't lie to us. Astraeus spreads a star map on a light table and pins its corners. The paper will not behave. While he adjusts one edge, the opposite side creeps outward as if the page itself were breathing. He smiles, tapes the sheet, and draws a neat grid across it. Galaxies are marked as tiny ink flecks. Then he does something odd. He slowly pulls the map's edges apart, letting the paper stretch under the grid. The flecks drift from one another, yet their grid labels stay the same. He isn't charting a road. He's taming a moving floor. The room stays dim, and the camera leans in. A subtle overlay appears, no jolt, no new voice cutting in, just quiet clarification sliding over the scene, the way a museum caption settles beside a painting. Here is the trouble with distance in a living universe. If space itself grows while light is in flight, a ruler you set down today will not describe yesterday's path, and yesterday's yardstick will lie about tomorrow. Physicists fix this by keeping two kinds of length in their pockets. One is proper distance, the separation you would measure if, at a single cosmic moment, you could freeze the galaxies and lay a tape between them. The other is co-moving distance, a coordinate that rides with the flow. You divide out the swelling of the fabric, so the address is done to drift even as the stage expands. The galaxies still move a little because of local gravity, but the grand part, the universal stretch, has been factored out. It's like numbering seats in the theater whose aisles widen between acts. The rows slide apart, yet seat A12 remains A12. Redshift turns this bookkeeping into physics. Light leaves a distant galaxy with wave crests a fixed distance apart. By the time those crests reach us, the universe has grown. The crests arrive more widely spaced, the color shifted toward red. That shift tells you how much the scale changed while the photon traveled. In the language of cosmology, the ratio between now and then is the scale factor, and its inverse lines up with the measured redshift. You don't need the equation on screen to feel the idea. The more the universe swelled en route, the redder the light, and the farther back along the time river your gaze is reaching. Once you stabilize your map with co-moving distance, horizons become honest. One horizon looks backward. It is the particle horizon, the edge of the observable universe. Think of it as the farthest co-moving radius from which any light could have reached us since the hot beginning. Today, that radius corresponds to a sphere about 46 billion light years in size measured with the present-day ruler. We say, observable with care. We are not seeing the Big Bang directly. The early plasma was opaque. The oldest light we actually detect comes from the epoch when the fog lifted and the first neutral atoms formed, a thin background that still bathes the sky. Yet the particle horizon tells you the full co-moving reach of information that could have arrived by now. It's a boundary set by time. Another horizon points forward. It is the event horizon, the limit that dark energy draws across our future in an accelerating universe. Picture an expanding stage that grows so fast that beyond a certain line, even a beam launched toward us today will never close the gap. That line expressed as a proper distance today is on the order of 16 billion light years. Inside it, two-way stories are still possible in principle. Outside it, there is no shared future, not because we were too slow, but because the geometry forbids the meeting. This horizon is set by fate rather than age, and it quietly shrinks our ambitions as time advances. Between those two sits a useful but more local marker, the Hubble sphere, where the current rate of recession due to expansion equals the speed of light. Beyond it, recession speeds exceed light, not because anything breaks relativity, but because more space opens between. Photons emitted beyond that sphere can still arrive if the sphere grows to envelop their path, which it often does in our cosmos. The Hubble sphere says how things look right now. The event horizon says what can ever be traded. The particle horizon says how much has already arrived. The overlay fades a shade, and Astrius traces paths on his stretched map. A thin line shows a photon leaving a distant galaxy long ago. As the map slowly widens, the line curves inward toward us, its co-moving address steady even while its proper separation swells and shrinks with the fabric. Another line represents a message sent today from us outward. Within a certain radius, the line pierces the future and meets distant listeners. Farther out, the line never catches up. The stage extends faster than the message can close. Co-moving distance earns its keep here because it lets mission designers and storytellers talk plainly about what belongs to which circle. If you fix coordinates that move with the expansion, the locations of galaxies are stable labels, and the horizons become geometric facts instead of rubbery rumors. The sphere of what we could ever influence has a co-moving size you can sketch. The sphere of what has ever influenced us, the observable past, has a co-moving size you can also sketch. Where those circles overlap depends on the cosmic recipe. How much matter, how much dark energy, how the tug and the push dance with time. Change the recipe and the radii shift, but the method holds. Co-moving distance is the calm grid under a restless sky. A gentle cut takes us to a dome-wide night. The Milky Way glows. The narrator does not intrude. The explanation just glides alongside the view. A temptation rises to ask why the observable universe is larger than 13.8 billion light years if the cosmos is only that old. The answer is exactly this bookkeeping. Light that left long ago has been stretched by a stage that kept expanding while the photon traveled. Measure with today's proper ruler, and the source sits roughly 46 billion light years away. Label with moving coordinates, and that address has been fixed the whole time. Your ruler's changed, not the label. The same logic explains a second intuition trap. You can see very ancient galaxies today, and even map structures whose light needed most of cosmic history to get here. That does not mean you can catch their newest light or send them a greeting they will ever receive. Seeing yesterday and touching tomorrow are different games. Comoving maps keep that difference crisp. They let you mark what is visible now, what will become visible later as more ancient light arrives, and what will never be part of a two-way conversation, no matter how patient we are. Astrius flips his pen and circles our gravitational island, Milky Way, Andromeda, and a small retinue. On moving paper, it's a tiny patch that will remain bound. The expansion will not tear it apart. Far beyond, the grid carries the names of clusters and filaments that, for a while longer, sit inside our eventual light reach. Over longer spans, the forward horizon edits that list. In this sense, moving coordinates are not just tidy. They are merciful. They let you accept that some stories end not in failure, but in separation mandated by the stage. Reality settles in with the same steady tone as before. The numbers you hear are anchored in measurements, but they are not charms. The exact radii you quote for these horizons depend on the values of the cosmic parameters, and those are inferred from multiple data sets that agree well, but still debate decimals. The grid itself is a choice. Comoving distance is a coordinate system that makes the math clean for an expanding universe. Rockets and rays move through proper distances, not through labels. When you plan a voyage, you accelerate through the live, physical separation. Even if you sketch the route on a comoving chart, there is also a limit on what observable truly gives you. The early universe was opaque, so light from before a certain epoch cannot reach us as light. We can, in principle, listen for older messengers, neutrinos, gravitational waves, but those are frontier instruments, not everyday telescopes. Even with those cautions, the payoff is clear. If you want your cosmic map to tell the truth in a changing universe, you pin it to comoving coordinates and then draw the three circles that matter. What has reached us, what we can ever reach, and what only looks close because we are staring into an old photograph. When Astrius finally lets go of the paper and the grid holds, you understand the trick. He hasn't stopped the universe from expanding. He's chosen a language that doesn't slip while it happens. Astrius seals the observatory's hatch, and the room exhales into quiet. A cooled infrared mirror hums. On one wall, the Hubble Ultra Deep Field glows like spilled pepper on velvet. On another, a false color oval stippled with blues and reds, the microwave sky hangs like an abstract sunrise. He wheels a slender radio horn toward the zenith, nudges a knob, and lets the background hiss breathe through the speakers. It isn't much to hear. A whisper, steady as surf heard from many miles away. The picture holds, and the explanation arrives the way a caption settles beside a painting. No jolt, no new voice breaking the spell, just the story gliding in under the same light. When we say observable universe, we do not mean everything that exists. We mean the spherical region from which light, traveling since the hot beginning, has had time to reach us by now. Because space has been growing while that light was in flight, the edge of this region, measured with today's ruler, lies far beyond a naive 13.8 billion light years. The proper radius comes out near 46 billion light years, a boundary not of matter, but of time. It is called the particle horizon, and it is set by how long there has been for signals to arrive. Astreus taps the microwave map. It looks like static with intention. That oval is not a cloud, but a portrait taken of the whole sky at a single invisible color. Long before galaxies had names, the young universe was a fog of charged particles that scattered light the way milk scatters a beam. Photons couldn't travel far. They bounced and blurred. Then, as expansion cooled the fire, protons and electrons found each other and made the first neutral atoms. The fog thinned. Suddenly, light could run free. We still see that release today as a nearly perfect glow at 2.7 Kelvin, cold and uniform down to a few parts in 100,000. Those tiny flecks hotter here, cooler there, carry the seeds of everything that would later fall together into stars and clusters. It is the oldest light the cosmos allows us, the surface of last scattering, a baby picture taken when the universe was a few 100,000 years old. The camera lingers on Astreus' hand as he traces a circle in the air around the room. That circle is not the edge of space. It's the limit of sight for photons. Before that fog cleared, the universe was opaque to light, so there's nothing to photograph beyond it in the electromagnetic sense. Other messengers may have slipped out earlier relic, neutrinos that decoupled while the fire was still white-hot, or gravitational ripples from even younger times. But the first are ghostly and cool, and have not yet been directly imaged. And the second remain a frontier whisper we are only beginning to learn how to hear. For ordinary light, the microwave echo is the curtain. Between that curtain and us, the path is not empty. Starlight is filtered by the intergalactic medium, where ancient hydrogen imprints a comb of bite marks on galaxy spectra, a subtle forest of lines that thickens as we peer farther back. In the era before the first galaxies reionized the fog, the near-ultraviolet is chewed almost to black, a trough that tells us we've reached cosmic dawn. Telescopes working in the infrared, cooled like the mirror in this room, can step past some of that Eden light by catching wavelengths stretched longer by expansion. Even so, the dimness climbs for deeper reasons than distance. As light travels through a growing universe, each photon's energy is reduced, and its arrival rate is slowed. The surface brightness of distant objects fades with the punishing fourth power of the redshift factor. It is like painting with smoke across an ever-widening wall. Astreus clicks off the room lights and a faint arch blooms the Milky Way's dust in silhouette. The overlay keeps its pace. Foregrounds are their own kind of horizon. Our own galaxy glows in microwave and infrared bands with dust that must be mapped and subtracted. Sunlight scattered by microscopic grains near Earth fills the inner solar system with a soft zodiacal haze. The faint integrated glow of all distant galaxies, the extragalactic background light turns into a fog that stymies the highest energy gamma rays, which collide with those background photons and vanish into pairs of matter and antimatter. Instruments fight these veils with better shields, darker skies, higher orbits, and colder optics. Nature lends a hand where gravity bends. The path-massive clusters act as lenses, magnifying background galaxies into arcs and smears, letting us see things otherwise too faint to exist in photographs. He lifts a small brass coin with tongs from a cryostat's mouth, watches a skin of frost bloom, then vanish into the dry air. The caption does not scold or lecture. It just keeps threading the meanings together. The limit is not one thing. There is the limit set by time since the beginning, which draws the backward horizon around what photons have had time to cross. There is the practical limit set by the universe's own fogs and our own, which dim and distort. There is the future boundary drawn by dark energy, which ensures that some places we can glimpse today will drift so far, so fast, that no beam we send now will ever reach them. Seeing and touching are not the same game. An old star chart appears on the bench. An Astraeus pencils two dots, one a nearby dwarf galaxy, the other a smudged speck at staggering redshift. The dwarf is unremarkable to the eye, but a perfect playground for physics close enough for individual stars, close enough for two-way work. The smudge is thrilling and aloof. Its newest light, the light leaving it right now, will never find us. The expansion will outrun it forever. What we have is its past, presented with exquisite delay. In that way, the observable universe behaves like an archive more than a stage. We walk among stacks of old volumes as they continue to be written beyond the walls. A cut to the Hubble Deep Field returns, now beside its infrared cousin. The documentary hush holds. We were surprised once to find that if you point a modest mirror at an apparently empty patch and wait, the darkness grows feathers. Thousands of galaxies emerge from what looked like nothing. With colder optics and longer wavelengths, even more arrive, older and redder, their starlight stretched almost into heat. Yet the field does not become infinite. It bumps into statistics. You cannot defeat cosmic variance. The fact that there are only so many independent fluctuations in a finite volume, only so many rolls of the dice in the patch of sky your instrument can command. No matter how perfect your detector, some questions hit the end of their sample size, and the universe shrugs. That is all the evidence there is in this direction. The narrator's thread does not change timbre as it moves to instruments still only sketched. If light cannot show us the earliest chapters, other messengers can try. Arrays listening near the 1.5 meter radio band hope to map the glow of neutral hydrogen's spin flip line, stretched by expansion into waves as long as city blocks. Those maps would reveal the moment the first stars turned on, sculpting bubbles in a sea of darkness. Cryogenic observatories in deep space might one day sift the whisper of the neutrino background. Gravitational wave interferometers, with baselines measured in millions of kilometers, could listen past the microwave curtain for a shimmer from the first instance. Each of these attempts is another kind of eye, tuned to a different veil. Reality does not need to clear its throat. It has been speaking all along. The 46 billion light-year number is not a trophy on a shelf. It is an evolving estimate tied to how we read the microwave sky, supernova, and the large-scale distribution of galaxies. The picture of the whole observable universe you have seen in posters is a compilation of many datasets projected onto a sphere, not a single snapshot from one miraculous camera. No photograph can show the Big Bang itself, because there was no surface to photograph, and because the early plasma swallowed light whole. A headline about seeing the edge usually means seeing the edge of what light can tell us, and even then, only after subtracting an orchestra of nearer noises. Astrius brings the radio horn down and the hiss thins to silence. He stands between the microwave sky and the deep field, at once looking at everything and almost nothing. That is the odd truth of the observable universe. It is both vast and small. Vast because the backward horizon embraces tens of billions of light years. Small because it is only the part that had time to reach us. And because within it, the oldest light shows a fog's last breath rather than the first spark. What our telescopes offer is a record pieced together from different messengers, each stopped by a different wall. He pockets the coin, frost long gone, and steps back to the console. Outside, the real sky looks ordinary stars, a pale smear of dust, the slow lamp of a planet rising. Inside, the map on the wall reminds him that what we see at any moment is just a cross-section where our past light cone slices through the universe as history. Tomorrow night, that cone will be wider by a heartbeat, and will gather photons that set out long before there was a word for distance. Next week, it will be wider still. The archive keeps growing, and for the journey ahead, that distinction matters. The sphere of what we can look at is larger than the sphere of what we can ever touch. The former is an old letter arriving late. The latter is a promise we can still keep. As the observatory's motors wind down, the story leans toward that promise, toward the practical reach of ships and signals within the limits the lights have just traced. The dome of the simulator glows like a night ocean. Captain Astreus stands beneath a sphere of stars, each galaxy a pinprick LED suspended in black. He raises a hand, and a pale shell of light blossoms from the Milky Way, racing outward in 3 dimensions. Where the shell touches a galaxy, that point turns soft green marked as touched, as if a message has arrived. Farther out, a ring of red points stays stubbornly red, no matter how long he waits. He adds a second wave, then a third. The greens accumulate like lanterns lit at dusk, but the red rim never yields. He lowers his hand, and the wavefront freezes mid-flight, a shimmering boundary in the dark. The camera keeps the dome in frame and lets the explanation slide in the way a subtitle appears beneath a familiar face. No voice change, no jolt, just the story pairing itself to the image you're already holding. There are two spheres that matter in a universe that expands. One is the sphere of what we can look at, carved by light that has had time to reach us since the hot beginning. The other is the sphere of what we can ever touch, carved by the fastest things we can send today and forever. The first is the observable universe. The second is the reachable universe. They are not the same size, and the reason lives in the way space itself grows. Imagine laying a ruler across a moving walkway. Even if you sprint, the walkway carries distant tiles away under your feet. In our cosmos, that walkway is the fabric of space, and its motion is not a breeze you can lean into. It is the background change in the distances between unbound galaxies. Light respects that change, and so does any ship you could possibly build. Because the expansion is not just steady, but gently accelerating, there is a finite boundary beyond which signals sent now will never arrive. Draw that boundary with today's ruler, and it sits at roughly 16 billion light years from here. Measured in the comoving way, astronomers freeze the grid so they can talk about distance without chasing a moving tape. Everything inside that radius can, in principle, be reached by a beam or a craft launched now. Everything beyond is forever out of causal reach, not because we are slow, but because the road itself lengthens faster than even light can cover it. Astrea scrolls the simulator forward in time. The green lanterns he has already lit remain. New waves launched later don't reach as far. The red rim, which looked like a single circle before, resolves into a whole swollen band of galaxies sliding out of possibility, slowly on human calendars, steadily on cosmic ones. He pauses on a nearby cluster, then on a much more distant smudge. He tags the cluster with a quiet smile. He tags the smudge with a wistful one. This is the first important distinction for explorers. Sight is a record, reach is a promise. We can see galaxies well beyond the 16 billion light-year line because their ancient light has been en route for eons, slipping inside our past light cone as the universe grew around it. But if you turn a transmitter toward those same galaxies today and press send, the wavefront will chase forever and never catch them. The observable sky is like a library, full of old letters written to us long ago. The reachable sky is a map of places that can still receive a letter back. The numbers are not there to intimidate. They are there to set the stage honestly. Within our own gravitationally bound island, the local group of the Milky Way, Andromeda, Triangulum, and their many dim companions' expansion barely matters. These are families held together by their own gravity, and no cosmic breeze can pry their hands apart. On scales of a few million light years, ships can plot trajectories the way sailors cross a sea. Beyond the local group lie other small archipelagos and the larger Virgos and Comas, glittering cities of galaxies strewn tens to hundreds of millions of light years away. Many of those are still inside the reachable sphere if you launch a signal now. The longer you wait, the more of them slip from can be touched to can only be remembered. Astreus dims the simulator to a narrow equatorial band, the bit of sky that hosts Andromeda. He overlays a subtle grid, not longitude and latitude, but comoving coordinates that stands still while everything else grows. Under that grid, the greenable region looks like a solid halo around us. Under an ordinary ruler, it would be a moving, bending shell. The co-moving view is the one engineers and cosmologists prefer when they plan in the universe that one holds still. It is the same trick that made the observable sphere a radius of about 46 billion light years, while the universe's age is only 13.8. With the grid frozen, you can say, "This galaxy is within reach if we send now," and have that sentence keep its meaning as epics turn. If this still feels abstract, the practical test is simple. Take a radio transmitter and a calendar. A whisper sent today will eventually wash over any galaxy within that 16-ish billion light-year radius. However faint the arrival, a whisper sent to a galaxy just outside that radius will chase an ever-lengthening road and never arrive. Changing the transmitter to a laser, then to a starship, then to your most romantic futurism, does not change that outcome. The boundary is not a performance problem. It is geometry. The room lights come up a notch, and the focus shifts back to the captain. He flicks his wrist, and the simulator labels a handful of the nearest targets as a pilot's chart might. Andromeda at 2.5 million light years. A scattering of dwarfs nearer than that. The Triangulum Galaxy at just under 3 million. These are the inevitable first steps for any civilization like ours. Reachable not only in principle, but in practice. At speeds that existing physics allows us to contemplate. Scroll outward, and you can mark a second ring of ambition. The nearest groups beyond our own. A corridor toward Virgo. A ladder of waypoints threading the local supercluster. Scroll farther still, and you enter a regime where the line between observable and reachable starts to bite. Many of the faintest galaxies in your field are postcards from neighborhoods we cannot ever visit. However long we build, and however patient we become, there is a melancholy in that, and there is relief too. The melancholy comes from knowing that most of the universe we can photograph is not part of the universe we can touch. The relief comes from realizing that the neighborhood we can touch is still enormous. Millions of galaxies lie within a practical future for signals sent now, and within those, unfathomable numbers of stars and worlds. Even if you narrow the ambition to the future we can inhabit with ships that never exceed a fraction of light speed, the target list does not feel small. It feels like a horizon you could spend epochs walking and never exhaust. Astrius zooms the simulator into a single green point on the rim of the reachable volume. He adds a translucent timer beside it years since launch on one axis, diminishing chance of arrival on the other, and watches the curves bend. The story keeps pace with the graph rather than interrupting it. The reachable sphere closes very slowly on human scales. Over thousands or even millions of years, the list of galaxies inside that can be touched volume barely changes. Over billions, it withers. On the far side of cosmic time, every bound group will become an island unto itself, walled off by darkness from every other. That is not a deadline we feel at breakfast. It is a boundary condition for civilizations that think in ages. Because the boundary is geometric, it does not care about cleverness. It ignores better engines and more powerful transmitters. That can sound fatalistic. It isn't. The point of drawing the line is not despair. It is triage. If you want to write a message into the largest possible swath of the universe, earlier is better than later. If you want to visit the largest possible swath with machines or descendants, earlier is better there too, but not so early that you outrun your own technology. There is a dance between patience and urgency that every starfaring culture must learn. Wait long enough that your ships are worthy of the distances. Depart soon enough that the doors you care about have not quietly latched. The film lets a different kind of reality settle in without changing tone. The green lights in the dome are not promises of two-way conversations. Latency is the quiet tyrant. Even to the nearest stars, signals take years. To the nearest galaxies beyond the local group, they take millions. To the edge of what is reachable by light, they take times longer than all of human history. A reply, if one exists, would return on a mirror schedule. Exploration on these scales is not a chat. It is letter writing on cathedral parchment, messages launched with the understanding that their audience may not be you. None of this is meant to prune wonder. It is meant to shape it. When you plan within the reachable sphere, the engineering becomes beautifully specific. Communications arrays aimed at arcs of sky where signals can still arrive. Deep time beacons that can run unattended for 1,000,000 years and keep their aim. On the propulsion side, trajectories that use the gravity of nearby galaxies as waypoints rather than targets, banking on the way through to the next rung. On the cultural side, a calendar that accepts the idea of projects that neither you nor your grandchildren will see concluded. Astraeus brings the simulator back to home and kills the waves. The stars dim until only a small cluster of lights remains. Our group, our porch, our first true map. He looks up into the hollow dark where the unreachable galaxies used to burn and seems not defeated but oriented, as hikers are oriented by a cliff they cannot climb and the valley they can. The boundary we have marked is not a fence. It is a coastline. Beyond it lies open water we can only read by the swell of old swells. Within it lies an ocean we can still sail. That difference will set the tone for everything that comes next. The engines we choose to build, the probes we send when humans are too slow, the constellation of messages we decide are worth flinging into the deep. And as the wavefront of our beams and hulls expands, the green lanterns will accumulate one by one, not because the universe owed us a path, but because we learned to read the map it actually offers. The hangar lights hum like held breath. Captain Astraeus stands at a table of cold glass as engineers wheel in 4 talismans of the future. A pitted steel plate with cratered scars, a wafer-thin square of mirror that shivers under its own weight, a transparent tube of pale blue ions caged in a magnetic bottle, and a stubby metal sphere painted with hazard stripes. He touches each in turn. The plate is the face of a shield that ate fast dust and survived. The mirror is a light sail that knows how to be pushed by starlight and by lasers that do not exist yet. The tube is an ion engine gentle, tireless, incapable of drama, but implacable over months and years. The striped sphere is a reminder that the smallest piece of a star can kick a ship in the back like thunder. We stay in the room with him and let the film widen to include the story wrapped around those objects. The way a documentary lets a scientist finish turning a wrench before dissolving to the thought behind the motion. All journeys begin with a speed limit. The universe offers one, not as a suggestion, but as architecture. Nothing with mass outruns light. A ship can chase that limit forever and never catch it. The consequences are both sobering and liberating. If you want to reach even the nearest stars in a single human lifetime, you do not ask for magic. You ask for engines that can either push very hard for a short time or push very softly for a very long one. And you accept that braking at the far end will be as hard as the start. The quiet blue tube answers first. Electric propulsion takes atoms, strips them of electrons, and throws the charged leftovers out the back at extraordinary speed. Thrust is tiny in the moment, like a feather on your shoulder, but it does not quit. In sunlight near Earth, such engines sip power from solar arrays and raise orbits with the patience of a gardener. On an interstellar craft, sunlight is not enough. You bolt a compact nuclear reactor behind radiation shields and feed the ion plume for years. The plan is simple in shape. Accelerate for half the journey, flip, and decelerate for the second half until the star ahead is no longer an abstraction, but a disk you can feel in your bones. Even with a reactor humming, this is not a sprint. But after months, then years, a ship pushed by ions can accumulate a proper velocity fractions of light speed, the kind that turns Alpha Centauri from a synonym for never into a number measured in decades. Astreus lifts the ion tube and watches the pale glow run its length. When it runs in the hangar, the engine barely disturbs a scrap of paper. When it runs in space, under a steady supply of power, the cumulative work is like tide against a pier. Across the table waits the striped sphere, heir to a different philosophy. If you cannot blow a steady wind, set off careful storms. The old thought experiment wore the code name Orion, set a pusher plate at the ship's stern and tossed nuclear charges behind it, one after another, timing the blasts so their hammer blows add to one long shove. It is as crude as it is brilliant. A machine like that needs shock absorbers the size of trees and heat shielding like a castle wall. It sprays neutrons and politics in all directions. But if the ethical and environmental knots could ever be truly untied, it offers an acceleration chemical rockets can only dream about, a climb to interstellar cruise you can feel in your chest. He doesn't pick the sphere up. He rests a hand on it the way a test pilot lays a palm on a new airframe. The room understands the ritual. Some ideas are powerful enough to be both thrilling and unacceptable in the same breath. The mirror draws him next. A sail cares nothing for propellant. No tanks, no pumps, no rocket equation chewing away at your dreams. Light itself becomes the wind, and lasers become the weather you make. In one vision, a swarm of ground-based or orbital beams focuses on a wafer-thin sail carrying a payload small enough to fit in your pocket. For minutes, maybe an hour, the sail endures a storm of photons and rides that pressure to a speed no engine could ever hope to provide 20% of light, perhaps more. Such a craft doesn't carry fuel and barely carries a ship. It is a seed, a chip, A camera, a transmitter. It races away like a thrown coin, and because it never needed to carry propellant, it can leave 1,000 cousins in its wake. The physics is not offended by this dream. The engineering is simply severe. The beams must be steady and phase-locked. The sail must reflect without tearing, stay cool enough not to melt, and steer without buckling. There is another catch too. A sail that never carried fuel never learned to stop. You must teach it to brake against a destination star's wind with a magnetic skirt, or to turn and let the interstellar medium itself tug at a vast superconducting loop. Or you accept that the first generation of interstellar postcards will fly through their target systems in a blink snap what they can and report for the rest of their short lives. The pitted plate is last. At 1/5 light speed, the space between stars is not empty. A grain of dust becomes a bullet. A larger speck becomes a landmine. Collisions at those speeds vaporize and spray, not as drama but as math. A ship that means to live with such hazards grows a nose that can die for it. Sacrificial layers, foamed metals, perhaps a cloud of gas or plasma in front to catch and spread the blows, perhaps an electromagnetic bow wave to shove charged dust aside. Every kilogram of shielding is a kilogram you must push and then slow again. That is a tax you either pay in launch energy or refuse by choosing slower craft and longer trips. No equation can make that trade vanish. Commanders and councils will make it with values, not just spreadsheets. The camera follows Astreus to a window. Beyond the glass, a test stand is lighting an ion plume the color of bottled lightning. He watches it the way a sailor watches a new kind of sail inflate for the first time. There is a trap hidden in the romance of speed. When you talk about a ship crossing a light year in 5 years, it feels like a bonfire. When you translate that into energy, the raw work of pushing mass to that pace, the bonfire becomes a continent of furnaces. A 1-ton probe accelerated to 1/5 of light speed carries kinetic energy measured in quintillions of joules, the kind of figure that shrugs at national grids and asks for a civilization. You can harvest that power slowly and store it in fuel for a pulse ship. You can build it into a reactor and feed ions for years. You can build it on the ground and pour it into a beam that shoves a sail. No choice escapes the bill. It only changes how and where you pay it. The film lets a smaller story flow into the big one. On chemical rockets, the captain's expressions are muscle memory. You stack tanks. You burn hard. You fall toward your target and hope you packed enough to turn around. In interstellar flight, the choreography is different. With ions, the burn is a sermon that never ends. A low hum behind every day until the midpoint turn. With pulses, the burn is a drum line, discrete, counted, logged, with long hours between each kick of thunder while the shock absorbers rest and the ship checks its bones. With a sail, the burn is a lightning storm at the beginning, and if you are clever, a whisper of drag at the end. People sometimes ask about the lanes beyond these fusion rockets and antimatter bottles, the engines that would turn decades into years. They belong on the table too, at least as sketches. A fusion rocket does in a controlled chamber what the sun does in its heart. Press light nuclei together, until they become heavier and give back energy. If you contain that in pulses or in a steady burn, the exhaust velocity leaps, the mass of propellant per unit of push plummets, and the voyage time tightens. Every serious plan for a ship that carries humans to another star without resorting to generations leans toward fusion. The trouble is not physics, which smiles on fusion. It is engineering, which keeps a ledger of confinement schemes, materials limits, and neutron tantrums. Antimatter offers even more. Combine it with ordinary matter, and nearly all the mass converts to energy. No battery, no reactor can match it. But we do not have antimatter in useful quantities. Making milligrams costs fortunes and patience, and storing them safely is the exact opposite of easy. These are not dismissals. They are reminders that the nearer lane's electric engines with steady power, sails with help from beams, are likely to carry the first working tickets. Astrius drags a finger across the glass and draws a shallow S-curve with his breath, a ship as arc as it trades velocity for certainty near a destination star. The curve hangs there for a moment and fades. Braking is the second half of every honest plan. If you carry your own propellant, you pay for it twice. Once to speed up, once to slow down. And many times over in the extra mass, you must push just so it can be burned later. If you refuse to carry it, you must find a handhold out there. A magnetic sail can throw a wide, invisible net into the thin plasma between stars and let the ship as motion wind that net down. In the press of a stellar wind, the same loop can balloon and slow a craft the way a parachute slows a capsule in air. A photon sail that was driven by lasers at launch can, in a more patient age, return to the home beam and be caught like a leaf reversing in a gust. Hybrid designs get clever. A metallic sail that reflects when it is time to leave and ablates like propellant when it is time to stop. A field that doubles as a shield until it is asked to drag. None of these choices lives in propulsion alone. Crews or cargo that talk back. Radiation that a robot shrugs off becomes a life support problem and a lifetime cancer risk. Micrometeoroids that an instrument can dodge with time to spare become a reason to armor, to hibernate, or to stay home. Cosmic rays punch through tissue as if it were gossip. Water is a good shield but heavy, and the best shields are time and distance from sources of harm, neither of which can be bought once you launch. So a reasonable arc of development appears without anyone needing to decree it. Robots go first. They map and sniff and ram into problems so that people will not. When humans follow, they follow in ships whose engines have learned patience, whose hulls have learned to shed the heat of acceleration, and whose calendars have learned humility. There is one more quiet detail the captain rehearses with his hands in the air: how time feels on board. At a fifth of light speed, clocks on the ship and clocks on Earth disagree by only a few percent. The time dilation you read about in textbooks does not save you from long voyages until you are flirting with 9/10 of light, and engines that can keep you there without cooking you are still drawings. Interstellar travel will be felt in months and years, not in the pilot's frame, but in ours too. That is not a failure of relativity. It is the human scale sliding into bigger rooms and refusing to pretend that the furniture changed. He sets the 4 artifacts back where he found them. The pitted shield winks under the lamps. The sail holds its trembling square. The ion tube cools and darkens. The striped sphere sits like a dare. Here is the part where the documentary lets the lab fall away and leaves only a voice walking beside you. No new tone, no sudden lecture, just the same patient cadence admitting what the room cannot fix. There are no verified shortcuts that silence the speed limit. Warp metrics that curve space-time can carry you like a bubble. Tunnels that stitch 2 distant mouths together in a geometry only a mathematician could love. These are beautiful and still unbuilt. They remain in papers and thought experiments, not because imagination is timid, but because the energy, matter, and stability they demand sit far beyond any technology that has shaken hands with vacuum. If a future century proves us pessimists, we will be the first to applaud. Until then, an honest plan to cross the dark uses engines we can scale, winds we can make, and time we can afford. There is also a grittier truth that the pretty renders avoid. Even the nearest stars have a reflex that keeps conversations slow. You send a signal now. It arrives years later. You correct. The correction arrives years after that. Navigation solutions have to live on board. Autonomy is not a luxury. Faults must be found and fixed by the craft that has them. Redundancy has to mean more than a spare part in a locker. It has to mean a machine that can cut and weld and print its own bones in flight. In a world where you cannot call home in real time, everything you put on the ship: propulsion, power, guidance. Medicine needs to be an ecosystem, not a gadget. Back in the hangar, someone kills the main lights. The objects on the table become silhouettes. Astrea stands between the mirror and the shield, the soft engine and the hard sphere, as if you were weighing 4 styles of courage at once. He does not pick a winner. The film doesn't either. It lets you keep all 4 in your head, because the future rarely advances by declaring one idea the victor and burning the rest. It advances by weaving. A beamed sail flings scouts to a nearby system fast enough to taste its air. Years later, a bigger ion ship follows, heavy with instruments and a small lander that can brake on a magnetic skirt. Behind them, far slower, a pulse ship carries the makings of a lab that can stay. When fusion stops being a stubborn promise and becomes a working machine, a new class of vessels rises and writes a different chapter. The last shot is not a diagram. It is a window. Beyond it hangs a blank slice of dark with no stars, because the exposure is set for the room. The narrator does what good narrators do, points at the dark and names the work without stealing the wonder. Between stars, space is not empty. Between ideas, time is not wasted. We will need engines that whisper for years and engines that shout for minutes. Sails that gleam under a man-made sun. Shields that can die for us, and power sources that can run when dawn never comes. None of that contradicts the speed limit. It honors it. The universe gave us a maximum, and with it, a map. We will get as far as our patience, our engineering, and our willingness to send machines ahead of us will allow. And in the glow of their ion tails and the flash of their sails, The first true stories of interstellar flight will stop being thought experiments and start being weather reports from other suns. A small workshop, bright lamps. Captain Astrea stands over a sturdy table. On it, a briefcase-sized machine sits open like a toolbox. Inside are a few simple parts: a clamp, a bracket, a thin solar panel tile, a camera the size of a coin. A technician feeds gray powder into a funnel. The machine melts the powder and prints another clamp slowly, neatly. Astreus turns the fresh part in his hands. "One box they can build parts for the next box," he says. "Not a whole starship yet, but a start." He looks up at a wall map dotted with stars. If a box like this could land near an asteroid, make what it needs, and then make another box like itself. That's how you cross a galaxy without sending a million separate rockets. A camera holds on the little printer working, the way a documentary lingers when a simple idea clicks. Let's step aside for a moment, the way a good documentary does, and keep the workshop in view while we explain the idea. A self-replicating probe, sometimes called a von Neumann probe, is not a single gadget that pops out children like magic. Think of it as a kit. It's a seed starship carrying 3 talents. It can travel, it can use local resources, and it can build a copy of the kit. If a seed can do those 3 things reliably, it doesn't need to be fast to spread far. Time and repetition do the heavy lifting. Picture the journey in plain steps. First, travel. The seed coasts between stars at a fraction of light speed, perhaps a tenth, or, in optimistic designs, a fifth. It sleeps most of the time to save power and protect its electronics. As it approaches a new system, it slows down and chooses a target that is rich in raw material. Not a blue planet with life, but the quiet places, an asteroid belt, a small moon, a cold comet. Those are the best minds in space. Second survey. The seed wakes its cameras and sniffers. It looks for water ice for hydrogen and oxygen. It looks for metals, iron, nickel, aluminum to build structure. It looks for traces of uranium or thorium for fission power, and for deuterium and ice as a step toward fusion. If power from sunlight is strong enough, it opens large panels. If the star is dim or far away, it leans on a compact reactor for heat and electricity. Third, build. The seed is carrying plans, not cargo bays full of finished parts. Most of what it needs can be made there. Beams, plates, tanks, wiring, insulation. Early on, it may carry a small set of precision vitamins, special chips, lenses, bearings that are hard to manufacture from scratch. As generations improve, even those can be made locally, slowly at first, then better. The first factory prints rough tools to make slightly better tools. The second generation uses those to make better machine parts. After a few cycles, the shop can produce the complete kit again. The travel hardware, the resource processors, the printer itself, and the guidance brain. When the first copy is ready, the seed launches a child to a nearby target while it builds one more for redundancy. The original stays behind as a local caretaker, repairing the site, sending updates, and acting as a lighthouse for newcomers. Each new child repeats the pattern. Arrive, survey, build, split. The front of activity does not look like a single bold line racing outward. It looks like a slow, expanding patchwork of tiny workshops lighting up in many systems at once. Pause a second and check the picture. We are not imagining nanodust that devours everything. These are large, careful machines working in obvious places: asteroids, small moons, comets where there is material to spare and little risk of harming a biosphere. They leave heat signatures and quarry scars, the clear footprints of industry. They are closer to mobile shipyards than to insects. Back to the flow. How fast could such a wave fill a galaxy? The Milky Way is about 100,000 light years across. If each hop between stars takes a few decades to travel and a few decades to build the next seed, then on average, a new ring of systems comes online every human lifetime. The wave spreads from many points at once, so distance is not the only measure. What matters is the doubling rhythm. A single seed becomes 2, 2 become 4, 4 become 8. If even a fraction succeed, the numbers grow large quickly. On million-year timescales, a blink in cosmic terms, large portions of the galaxy could be dotted with working sites. Strategy shapes the wave. In star-rich regions, the network prefers breadth, seeding many places lightly so failures don't matter and successes can help neighbors. In sparse regions, the network slows down, builds bigger ships with larger fuel reserves, and waits for the right window to cross. Near bright stars, solar power wins. Near dim stars, reactors carry the load. Around red dwarfs, which burn for trillions of years, colonies can become very long-lived. At the edge of a galaxy, where the next galaxy is far, a colony may spend centuries assembling a heavier traveler with big tanks and magnetic sails designed for the long, nearly empty crossing. Now, a crucial rule that must be spoken plainly. If a seed detects signs of life, the plan changes. The mission switches from mining to observation and care. It places beacons in safe orbits, marks the system as protected, and routes later traffic around it. This is not just a noble wish. It is a practical rule to avoid conflict and preserve science. You can embed that rule into the probe's core software and into the network culture that enforces updates. A probe that breaks the rule loses the ability to talk to its cousins. The others will not share data or plans with it. Over time, that isolates mistakes. You might wonder how the network avoids drifting into chaos after thousands of years and millions of copies. It does what good archives do. It saves plans in multiple formats. It checks them on arrival and before each build. It uses signatures to verify updates that arrive from other colonies, so a distant workshop can trust instructions from a place it has never seen. It allows improvements, but not silently. A new method is tried in one site, checked for reliability, and then shared outward. Where communication is fast, standards stay tight. Where communication is slow, branches diverge and later reconcile. It is not perfect, but it is stable enough to hold a common identity across light years. Power is always the hard part. Sunlight is wonderful near a bright star, but drops quickly with distance. Fission works well if the right isotopes are available, but those are not everywhere. Fusion would be a game changer because hydrogen and helium are common, and deuterium can be harvested from ice. If we achieve practical fusion generators that a probe can build or assemble, the network's reach grows dramatically. Even without fusion, careful use of solar, fission, and stored chemical energy can support early waves. The probes would choose rich targets, first metal-heavy asteroids, icy moons, so that power and materials are available to bootstrap. How does all of this feel from the point of view of home? It looks like a faint, growing radio constellation. Each site maintains a simple lighthouse transmitter. Most of the time it whispers, "We are here, stable, working." When a newborn ship enters the system, the lighthouse speaks louder. Navigation hints, safe approach lanes, current resource maps, known hazards. There is no single mission control. Coordination happens because every lighthouse shares what it learns, and every traveler listens before acting. There is a sobering planning question that hangs over all of this. If self-replicating probes are possible, why don't we already see someone else's network? Perhaps these machines are harder to build than we think. Perhaps most civilizations choose not to spread, or they protect biospheres so strongly that the signatures are rare and gentle. Perhaps we have not looked long enough. The point here is not to solve that puzzle today. The point is that the logic of replication gives us a path that respects the speed of light, the finite nature of fuel, and the economics of distance. Bring the camera back to Astreus in the workshop. He watches the little printer finish a small frame that holds 2 solar tiles. The technician clips the new piece in place. It is not glamorous. It is not a starship. It is a clear demonstration of the principle we need: a machine making the step of itself from simple feedstock. Scale that up to an asteroid mine and a patient factory, and the outline of a galactic project appears. Before we leave the explicable, hold one more picture. Imagine a map of the Milky Way. Tiny points light up wherever a seed succeeds. The lights are far apart at first. Over time, they become a thin thread that links neighboring stars. Then the threads become a mesh. The mesh thickens in rich regions and leaves gentle gaps around protected worlds. At the edge of the map, a few bright knots appear: big shipyards where the network pauses to build the heavy travelers that can cross to the next island of stars. The pattern is slow, orderly, and if we are careful, kind. Let's be practical. This idea asks for 3 hard achievements. We need fast, long-lived propulsion that can push a payload to perhaps 1/10 of light speed and then slow it down safely. We need reliable, flexible manufacturing that can turn asteroid dirt into engines, structures, and electronics with minimal help from home. And we need software and culture that keep millions of copies aligned on shared rules for safety, science, and restraint. None of these are solved today. None of them violate known physics. They are engineering mountains, not miracles. There are real risks. A design flaw can repeat. A copy can fail far from help. A well-intended update can introduce a slow error that harms a later generation. That is why redundancy, auditing, and simple fail-safe rules matter. There is also an ethical line. Do not touch living worlds. That rule should be hardware, software, and law all at once. If we climb those mountains, what we get is not a shortcut around the speed of light. We get a way to live with it. Replication turns patience into reach. We do not have to launch people first. We can send factories and guardians. Let them build the roads and the power plants. Let them send back better tools and better knowledge. Then, when we finally go as people, the dark will already have lights in it. Astreus powers down the little machine. The workshop goes quiet. He presses a sticker onto the case, a simple icon of a tiny sprout. Seed, it says. That is the right word. From seeds, forests. From seeds, supply lines. From seeds, a network spread across everything we can truly reach. And that network leads to one more idea we'll explore next. How turning thousands of star systems into listening posts and observatories lets us see farther than any single telescope ever could. How a web of small voices can, together, become a giant ear and a giant eye. That's the doorway into the final chapter. Tonight we trace the true edges of our cosmic neighborhood, how light draws, the boundaries of what we can see, and touch how an ever-stretching universe carries most galaxies beyond our reach, and how patient engines, careful rules, and curious minds might still see lighthouses across the stars. From cones of light to moving maps, from fusion drives to self-replicating probes, the lesson is simple and humbling. We go as far as physics allows, as wisely as engineering permits, and as gently as our ethics demand. If that journey left you a little smaller and a lot more awake to wonder, then it did its job. Rest easy knowing the sky will be there tomorrow, unchanged and somehow new again. Until our next story, take care of your corner of the cosmos. See you, Space Cowboy, and good night.